Okay guys, in the previous video we talked about the principles of Gauss Law, electric flask, and application of Gauss Law based on electric field. So in this video we are going to solve some questions applying the principles we talked about. So this is 2025 EE to 11. The first question states as I articulate. Calculate the value of the electric flask, which is phi E, through the surface of a sphere with radius 4 mm that contains a charge of 50 microcoulomb, which is positive, and 50 microcoulomb, which is negative, at the center. And it was supposed to be draw a simple sketch showing the direction of the electric field relating to charges in part 1 and part 2. So the first thing we are going to do is collect our data. So we are going to collect our data. So we are going to set data. So our data, we have been given the radius, which is 4 millimeters. Okay, so we are going to change into meters by dividing by 1000. So it will give me 0.004 meter. Yeah, then what else do we have? We also have the charges. So we have charge at 1, which was positive, okay, 50 microcoulomb. Then we also have another charge, which is charge 2, okay, which is a negative 50 microcoulomb. So from here, our first question is asking us to find or to calculate the electric flask passing through a surface which is a sphere, okay, with that radius and those charges. So here we are going to apply Gauss Law. So we know basically that a sphere, for us to find the electric field, it will take us to Gauss Law. So that's what we are going to apply here. So electric flask, which is phi E, is equal to the charge, okay, the total number of charges, then times epsilon. So here we are just replacing. So what's our charge? So our charge is 50, okay, then times epsilon, which is 8.85 times 10 to the power negative 12. Okay, from here I'll compute this. So when I divide, let me get my calculator. Okay, so here this is 12. So when I divide, I'm getting this. Okay, so we are going to round off to at least 3 significant figures. So my final answer would be 5.6. Okay, so this is a 4, so I'll round off to it will be 5, then times 10 to the power 12. So this will be our answer, and this is electric flasks, and the SI unit is what? It's Newton dot meter squared per coulomb. So we are going to have that. Okay, so now this is for charge 1. Okay, so this one is for charge 1. So for charge 2, on our Roman numeral 2, we are going to have the same charge, okay, because we just replace the charge there, but it will be negative. So we are going to have the same answer, but it will be negative. Okay, so we are going to have that, which is Newton per meter squared per coulomb. So that's how you go about it. Then our question is also asking us to find or to draw a simple sketch showing the direction of the electric field. So I think I talked about this in the previous video. I said electric field when it's positive, so you have a positive 50 charge, so which means the electric field lines will go outward. Okay, the electric field lines will go outward when it's positive. So when it's negative, it's the vice versa of this. So when it's negative, we have a negative 50. The electric field will go inward. So that's the direction. That's the simple sketch you can show. Okay, so we proceed to the next question. Okay, so the next question is telling us to find the, so let me just read through. Calculate. Okay, so we'll start from a positive line charge, which is on B, a positive line charge with the density of which is 75 nano coulomb per meter, okay, is at the center of a Gaussian cylindrical surface with the radius of 0.35 meters and length of 1.5 meters. Calculate the following. So the first question is calculate the total charge enclosed by the Gaussian cylinder. So now what must come in our mind is we must take note of the type of equation we are dealing with, by taking note that it's what, it's a cylinder, a cylindrical surface. Okay, that's what we are dealing with. That's what we are dealing with. So here we are going to apply the equation of a Gaussian cylinder. So we said from our previous video that we can find the electric field by linear charge density over 2 pi r epsilon not, like that. Okay, but here they don't ask, the first question is not asking us to find the electric field, but is asking us to find what, the total charge enclosed by the cylinder. And we said this, which is linear charge density, is equal to what? Okay, we said it's charge over length. So we are going to compute this to have charge is equal to that times length. So this is the formula we are going to use. Okay, so this is the formula we use in the first question. Okay, so charge is equal to linear charge density times that, and from our data, we can correct our data. The linear charge density has been given as 75 nano coulomb per meter. Then the length has been given as okay, let's check. So that's that. Then the length has been given as what? 1.5. Okay, so we are going to replace on our formula. So we have 75 times 10, nano is negative 9. Then we are multiplying it with what? 1.5 meter. Okay, so let's compute this. So I'm having 0.0000001125. So we can take it into standard. We can move the points 1, 2, 3, 4, 5, 6, 7. So we can have 1.125 times 10 to the power, since it's going to the positive side, so we are going to have negative 7. So this will be our answer. So coulomb. Okay, so that would be our total charge enclosed in the Gaussian cylinder. So that's how to go about it in A. So let's go to B. So B, they're asking us to find what the electric flux through the Gaussian surface, okay, from the infinity line charge. So electric flux, okay, electric flux. So we are going to apply the formula for electric flux, which is by applying Gauss law. Okay, so we are going to have charge over A naught. Okay, so our charge is the one we are from finding here, so we'll replace, okay, which is 5 times 10 to the power negative that over 8.85 times 10 to the power negative 12. Okay, so now we are going to compute this. So when I compute, I'm getting that answer. So so take it into standard 1, 2, 3, 4. So we're going to have 1.2 so I'll leave it to 3 significant figures, so I can leave it here, then I'll say times 10 to the power 4. So this is electric flux, which is Newton per meter squared coulomb. So this would be our answer. And by the way, I want to ask, like, why have we not used this formula? Why did we not choose the formula, which is E is equal to A equals that? So why have we not choose this to find the electric flux, but we are using this? So you have to differentiate between these two. Okay, so here we are talking about Gaussian surfaces, and we are unable to find the area. Okay, like a cylinder, a wire, a sphere, and a sheet. We use this formula. This formula only applies when you have a surface where you're capable of finding what the area. Okay, so that's why we're using that formula. I hope it's clear. So electric field of a cylinder, we have that formula, which is lambda. So that's lambda, okay, over 2 pi r epsilon 0. So we are going to replace, then we compute. So our charge has been given in the question, okay, which is 75. I mean the linear charge density, which is 75 times 10, which is nano, which is negative 9 over so we're going to have over 2 pi r is 3, and epsilon is 8 times 8.85 times 10 to the power negative 12. Okay, so we're going to compute that. So when I compute, I'm having that, it has gone, so I'm having that. So this will be my answer, which is electric field is equal to 449.6. okay, so Newton per coulomb. So that will be my answer. Okay, so that was 2024. So now let's look at 2025, how the question came. Okay, so this is 2025. So this was the question. Okay, so let me just read through. So the question reads as articulate. So give at least 3 reasons of a cylindrical Gaussian surface is ideal for analyzing the electric field of an uniform linear charge. Okay, so here we want to give 3 reasons why the cylindrical Gaussian surface is ideal for analyzing the electric field of a uniform linear charge. So what are they talking about? So they're talking about a linear charge. So here the best thing you have to understand, not just memorizing. So you have to understand what they're talking about. So I'll just draw something. So the first reason is that it matches symmetry of the line charge. So it matches symmetry of the line charge. So for example, if we have a wire, okay, if we have a wire like that, then this wire has some charges which it is charged, positively charged. So this wire is charged. So let's say we relate any point, maybe from the wire we have a point maybe there, which is point maybe J. Okay, so the electric field, like we said, of a positive charge comes outwards like that. So we are going to have electric field which will come at that point, and if we have relative points from the same wire, they'll come out like that. Even this side, they come out like that and like that. So that's what basically this means. It is symmetry of the line charge, that line charge. So here we are going to form something like a cylindrical surface, which is like that. Okay, so we are going to form something like that. So there is that symmetry between the line charge and the electric field, okay, of this cylindrical surface. So that's what that principle basically means. Then for the electric field is constant. So just from what I've drawn there, I'll draw it again here. If we have something which is like that, so we're going to have a surface which is enclosed like that. So here you will see that the electric field will be constant, because from the distance from the charge to there, from the charge to certain distance there, from a charge to a certain distance there, if you put it in 3D, the distance will be the same. So that's why the electric field will be constant. So from that charge to a certain point, from that charge to a certain point which you are relating to, okay, so it will be constant because the charge will be perpendicular to the point. Yeah, they'll be perpendicular at the same distance. Then basically the last rule which we can talk about, it simplifies Gauss law. Okay, it simplifies Gauss law. So these are the three reasons why a cylindrical surface is ideal. So those are the three reasons, but there are more, but these are the reasons you can talk about. Okay, so we go to B. So here B is saying we have using Gaussian law, okay, the total charge enclosed by the cylindrical surface, okay, where you have been given the radius as 4 centimeters, the length as 10 centimeters, okay, within the uniformly charged cylinder, okay, of radius that which is 5 centimeters, with the charge density of this one. So now we have to collect our data and analyze what we have, and they want the total charge. They want the total charge. So here what we are going to apply is okay, so just like we said on, so this is a cylindrical surface we are dealing with. So we said the formula to use is this one for electric field. Then we have the linear charge density. But here, if you check on the question, what we have been given is not a linear charge density. If you check the SI unit, this one is meter cubed. Then what we have here is meter squared. Then for the other one, which is for a sheet, it's meter squared, because that's area charge density which was there. So for this one, we have to analyze that it is it is in cubed, so we are dealing with volume, so we are going to call it as so the first one was linear charge density, so this one is volume charge density, where we're going to say the density, or that symbol, which is volume charge density, will be equal to charge over the volume. So this is the formula which we are going to apply. Okay, so now we are going to make our Q the subject. We are going to have that, then the volume. So now what's the volume of a cylinder? Okay, so the area of a cylinder, which is the same as the area of a circle, which is pi r squared. Okay, so for volume we'll just add an L so that we can have a meter cubed. Okay, for volume. So that's the formula which we are going to apply. So from this we have been given the volume charge density already as which is 3.0 times 10 to the power negative 6. So I've been given that, which is coulomb per meter cubed. So we just have to find the volume, which is pi. Okay, the radius has been given as 4 centimeters, so we have to take it in 2 meters, and the length as 10 centimeters, we take it into 2 meters, then we replace. So let's do that. Okay, so when I take it in 2 meters, I'm going to have a 0.04 squared. Then here I'll have a 10 into meters, I'm going to have a 0.1. So we are just dividing by 100. That's how we are changing this. So from here I'll multiply to find the volume. So I'm having that huge number, so I don't want to round off, so let me just do it direct. So let me just replace there. So let's replace there direct so that we find the answer at once. So we have this, which is 3 times 10 to the power negative 6. So we are going to multiply it with pi 0.04 squared, then 0.1. Okay, so I can now compute this. So I'm having a very, very small number there. So I'm having a 0.00000000015. So I'll make it into standard, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm going to have 1.5 times 10 to the power negative 9, which is coulomb. Okay, so that would be my answer. So now let's do the last question. So our last question is asking us to find or to determine the electric field at a point which is 4 centimeters from the axis of a cylindrical surface. Then we compute the electric flux through a Gaussian surface. So what we are going to do here, so basically we have two questions. So the first one, we have to find the electric field, then we compute the electric flux. So the electric field, we are going to apply the formula, which is let me just do this. So electric field of a cylinder, we said it's E phi, which is a lambda, then we're going to have 2 pi r epsilon 0. Okay, so we are going to have that formula, and we know that this is linear charge density, which is just a charge over L, which is length. Okay, so I'm going to replace there. I'm going to replace here. Okay, so I'm going to have charge over 2 pi r epsilon 0 then L. Okay, then our charge from where we are coming from, okay, from where we are coming from, I'm going to use this, okay, as my charge. So my charge is it is Q. We have this is the volume charge density, and you multiply it with what the volume. So I'm going to replace what volume is. So volume we said is pi r squared L. So I'll replace it now on charge. So on charge we are going to replace that. So when you replace that on charge, we are going to have that over pi r squared L over 2 pi r epsilon 0 L. So I'll cancel whatever is common. So I can see L, I can see L, I can see pi, 1 remains 1 r. So my final formula which I'll use, I'm going to have that r over 2 with the permittivity, like that, where we have been given the radius as 4 centimeters. So I'll take it in 2 meters, and we'll read off the volume charge density. Then we know the constant. So let's replace. So the volume charge density was 3 times 10 to the power negative 6. The radius is 0.04, then over 2 open times 8.5 times 10 to the power negative 12. Okay, sorry for that. So let's continue. So here when we compute this, what are we having? Okay, so when you compute it, you are going to have a 6.78 times 10 to the power 3 to the power 3. It is Newton per coulomb. So this is our electric field. So the electric flask, we are going to now apply Gauss Law to find the electric flask. So we apply Gauss Law where we write the formula for charges. Okay, so this is the formula to use our charge we found, you replace, then the epsilon 0 replace there. So let's try to compute. Okay, so when you compute, you are getting that answer. Okay, so which is 6.9. Okay, so we can leave it to 1 decimal place. Yeah, so this is this is electric flask, so which is in Newton meter squared per coulomb. So that would be our final answer. So you may comment in the comment section. The next subtopic I'll do under electrostatics. Thank you.